While computational modeling and simulation has had a wide range of application in the medical device industry, it's still not used as widely as it can be. And there are scientific and technical challenges that need to be overcome before that happens.
The biggest challenge, I think, in this field is validation. How to make a model not just be a good model that looks good and has good animations, but actually represents what's happening in reality. Without that representation, it's just not useful. You cannot test as much in the human body as, say, if you're developing a component for a car or for a hydraulic valve. If you look at the stiffness of skin, for example, or a muscle tissue, that is not as easy to determine as, say, the stiffness of rubber or glass or steel. And there's so much variability from person to person. So when you need to put these properties in a model, it's more of a challenge if it's a model in the biomedical field. And that is not easy to measure. So one of the things we do is to help the client actually do bench tests that are just designed to obtain that property by itself, and go and model that bench test and try to have a whole spectrum of tests that give us more confidence when we say that the thermal conductivity is that much. And without proper validation, the value of the simulation gets lost.
One of the big issues is how do you convince the decision makers that they want to go through this effort to verify and validate your computational model to demonstrate that it represents your reality or your context of use. ASME is a third party that's the bridge between what is the designer doing and what is acceptable for the regulator.
Simulations should facilitate and accelerate the development of the next round of great medical and biomedical achievements. For example, bioengineered organs. With simulation, they can do it faster, they can do it better, they can optimize it. It's limitless.